Number 18. It looks like we have a solution of NaCl. It's combined with another solution of MgCl2. What will be the molar concentration of chloride ions? Well, both magnesium chloride and sodium chloride are aqueous and soluble, so they're going to split up into their ions. We just have to figure out how much is in each one. So obviously we're going to need to know how many moles of chloride ions are in this one and how many moles of chloride ions are in this one. And let's try that out. So let's do the NaCl first. So we know that to find the moles, we can do molarity over liters. The concentration of the solution is 0.6 molar. It's 0.3 liters. And then we got to do a little bit of math without a calculator. So if I had 3 times 6, that would be 18. Agreed? But I'm not really doing 6. I'm doing one that's one place to the left of it. So I know that the decimal is going to be at least there. And I'm not really doing 3 either. I'm doing one place to the left of it, so I'm going to have to move it another. So it looks like it's going to be 0.18 moles of NaCl. So we'll get rid of that in this first one. And because there's only one chloride ion in the whole molecule, it's going to be 0.18 moles of chloride ion. Alright, so we're done with the first one. Let's do the second one in the same manner. Now that it's set up, we're going to have to do 0.2 times 0.4. Well, 4 times 2 is 8. And since we... well, you know what? Actually, we did the other one by decimal pushing. Let's do this one by scientific notation. So instead of 0.4 times 0.2, we're going to do 4 times 10 to the minus first, because that's this number in scientific notation, and 2 times 10 to the minus 1 is that one. Well, 4 times 2 is 8, and then we have to add the exponents because we're multiplying. So minus 1 plus minus 1 is minus 2, and that is the same as having a 0.08 molar magnesium chloride solution. Now, of course, there are 2 chlorines in each magnesium chloride, so it's actually 0.16 molar in chloride ion. So these are the 2 numbers that we need. Not molar, moles. We've been finding moles. And so we're going to add them together, and we get 0.34 moles right here. And it could be that answer, but you remember we're talking concentration here, so we've got to take, this is how many moles we've got to divide that by, oops, let's get our pen back. We've got to divide that by the volume. And the volume was 300 milliliters poured into 200 milliliters. It's a total of 500, so it's divided by 0.5. Now how do you deal with that without a calculator? Well, if we were doing 0.34 divided by a big number like 10, this would get smaller. But since we're dividing by a number that's less than 1, this is going to get bigger. And of course, if you divide by 0.5, it's going to get twice as big. So I think the answer to 18 is going to be C. Hey, if you're thinking, what the heck did 18 have to do with equilibrium? Aren't we supposed to be practicing equilibrium? You're right, there's no equilibrium here. They both completely dissociate. So it had nothing to do with equilibrium. It just seemed to be out of the blue. On to 19. Let's look at number 19. A student is mixing KCl and lead nitrate solutions, and a precipitate's formed. A reaction's going on here. They're going to be asking us about which ions are most concentrated. So let's draw a reaction so that we're clear about what's happening. So there's the reaction. I'm going to balance it. There's 2 chlorides on the right, so we got to have a 2 there, and we got to balance the potassium. So I think that's okay. The other thing is, let's write down the amounts here. We have 1 liter, and it's 1 molar KCl. We have 1 liter, and it's 1 molar of that stuff, which means we're going to have 1 mole of this stuff and 1 mole of that stuff. Now, if we're going to find out which ions are in highest concentration, let's make sure we understand what the limiting reagent is. So if we said that, that for every 1 mole of lead nitrate we needed 2 moles of KCl, well, we are using 1 mole of lead nitrate, and we don't have 2 moles of KCl, which tells you that this is going to be the limiting reagent, and this is going to be the excess reagent. Now that conflicts with one of the things they're saying here in the question. They say that nearly all of the lead ions disappeared from solution. And the reason I say that that conflicts is because the lead chloride over here is a solid, and none of those, because it's a solid, ions will be in solution. The only lead ions that could be in solution are from the reactant over here. And since they said that since we're figuring out that this is in excess, it can't be in excess by much, but we have actual amounts. So that's a little bit unusual. But let's look at our answer choices. So the one thing we know is we know that B cannot be right. Now, why? Well, they said that that this one, there was very little ions. There's very little of lead ions left in the solution. That's the only place they could come from. These are all precipitated. Now, the potassium chloride goes over to make potassium nitrate, and that stuff is aqueous. And because it's aqueous, it'll dissociate into potassium plus and nitrate ions, and there will be a lot of those floating around. So there cannot be more lead ion in there than potassium or nitrate. So B is out and C is out for that reason. Now to figure out if there's more potassium or nitrate, well, we found that the KCl was limiting, so there's not going to be any potassium left from there. All the potassium will be on this side. And so if we have 1 mole of potassium, let's say this is before, and let's do after, it's going to make 2 moles of potassium ions and 2 moles of nitrate ions. Now you might think, well, they're going to be the same. But we found that this lead nitrate was excess, so there will be some lead nitrate left in there, and so I think we're going to have some nitrate afterwards left over here. And actually we can figure it out. If 1 mole of potassium chloride is being used, then only half a mole of this stuff will be left, and so we're going to have 0.5 moles of nitrate left over here. So the nitrates will be left over from 2 different chemicals, and so I think there should be more of that. So the answer should be A. Number 20, the solubility of lead sulfide is that molar. What is the solubility product constant, KSP, for this? So hopefully at this point the KSP ones are becoming old hat, because we've seen a couple of them up to this point. And you know the tools we're going to need, definitely an equilibrium expression, probably an ice table as well. Hey, while we're here, let's play a little game. What did I forget in my reaction that would make me lose credit if I were being asked to draw a reaction for the solubility of lead sulfide? Well, I forgot the charge. That's right, I need a charge. It doesn't have to be balanced because it's 1-to-1 for each one of them. And we remember that these kind of ice tables tend to be really simple. We don't worry about the solubility or the concentration of this solid stuff, but the molar solubility is how much dissolves. And this number we know is 3 times 10 to the minus 14th molar. We know these increase by x, and so we are going to know those values as well. And our KSP is going to equal that. And you might ask, why do I draw out the general expression? Because I'm just making sure that I'm not forgetting exponents, or coefficients that would become exponents. Those are the things we tend to mess up. And now we got to do a little bit of math without a calculator. Well, 3 times 3 is 9. 9 times 10 to the, and then we add the exponents, so minus 28. So the answer looks to me like it's going to be D. Number 22 is a Le Chatelier principle question. They're asking us which one of these changes will increase the number of moles of I2 at equilibrium. So let's look at A, increasing the volume at constant temperature. So if we increase the volume, remember we've got some gases in here. If we increase the volume of the container, the gases can spread out. That will momentarily decrease the pressure, and more gases will get created to try to fill it. So it's going to shift to the side with the most gases. So if we shift the side with the most gases, let's see, we've got 3 moles of gases on this side and 3 moles of gases on that side. So no, we're not expecting it to shift either direction because we have the same number of moles on both sides. So we can pretty much rule out A, and we can pretty much rule out B for the same reason. Then we get down to C and D, we're increasing the temperature, and that all has to do with the energy. So if we want to make more I2, we're going to have to decrease the amount of energy, so the reaction will shift to the right. And if we do that, we should get more I2. So I think the answer should be D, decrease the temperature at a constant volume. I missed number 21, so let's go back to 21. For a particular salt, the solution process is endothermic. As the temperature at which the salt is dissolved increases, what will occur? And so I'm going to use sodium chloride as my imaginary salt. To figure out which way it's going to shift, we need to add energy to it. It's endothermic. It absorbs energy. So we're definitely going to want to put the energy in on the reactant side since it's absorbing it. And let's see what our choices are. So if we increase the energy, we're going to expect the reaction to shift to the right. And going to the right is dissolving better because it's splitting into its ions. If we shift to the left, it's precipitating and forming a solid. So if we increase the energy, it goes to the right, dissolves better. And that means it will become more soluble, not less soluble. So we can pretty much get rid of C right there. And let's see what our other choice is. If it goes to the right, that we're expecting the equilibrium to increase because the reason is the equilibrium constant is products over reactants. If you make more products, you will get a bigger equilibrium constant. So KSP should increase, so it looks like A, and the salt will become more soluble. So I think the answer here is going to be A. One last thing we should check is, do temperature changes actually change K or not? Well, they didn't have that answer. Oh, no, they did. KSP will not change. And that's not it, because temperature does actually impact K. All the other Le Chatelier principle changes don't. Number 23 tells us we have a sealed isothermal container. Iso just means same temperature here. It initially contained 2 moles of CO and 3 moles of hydrogen. So I've drawn out an ice table here. If it initially contains 2 moles of CO and 3 moles of H2, that's a good place to start. They're implying that it doesn't have any of this other stuff in it. We don't normally use moles in ice tables. We normally use concentration or pressure. And so we're going to assume that this is a 1 liter container because they didn't actually say, and we will use those numbers. Now, then they say at equilibrium there was 1 mole of CH3OH left in the container. What was the total number of moles of gas present in the container at equilibrium? Well, so since we have our initial amounts, we do know the equilibrium amount of CH3OH. It was 1 mole, which means the change was an increase of a mole, which means this one has to decrease by, you got it, 2x. And this one has to decrease by x. Since x was 1 mole, I'm going to have 1 mole of CO left. And since this is going to be going down by 2 moles, I'm going to have 1 mole of H2 left. And to figure out our total pressure in the container at the end, well, we got to make sure they're all gases. Yep, they're all gases. So it looks to me like it's going to be 3 moles in the end. So the answer should be C.